Children, yesterday we began studying about chemical reactions. Chemical reactions result in chemical changes, and those chemical changes we put them in the form of chemical equations. Once we write an equation in the form of words, we try to put it in the form of a formula. We use symbols. We try to learn more and more about that chemical change, and that is all the stuff we deal with in the field of chemistry. Yesterday we got a fairly good idea as to what these chemical reactions are and how they result in chemical changes. Today, let us try to study more about this. Mainly today we will deal with chemical equations, writing them down. Writing a chemical reaction in the form of words, it's an easy thing. There is no difficulty involved. Say we write magnesium plus oxygen, an arrow mark, gives magnesium oxide. What's the next stage? Magnesium is represented by the symbol Mg. Mg, I got it written here, capital M, small g. When it is written Mg, it is understood it is magnesium, it cannot be anything else. Because chemistry has drawn a list of all chemicals, the elements, compounds, and has got them designated by these symbols. Plus O2. I told you yesterday why we should write O2. Because oxygen atoms, they are all set in twos. Separate oxygen atoms are not found in nature. Two oxygen atoms come close, get into a bond, then you call it as oxygen molecule. Magnesium atom reacts with the oxygen molecule to give us, this aroma says, to give us magnesium oxide. It is capital Mg, small g, capital M, small g, then capital O. If you write small o here, it won't be oxygen. It has to be capital O because here it is capital O. When an element has a single letter symbol, the letter will be written in capitals. When an element has a two-letter symbol, the first letter will be a capital letter and the second letter will be a small letter. Now the question of balancing it. If you just write Mg plus O2 gives MgO, it is not enough. The reactants and the products, here only one product. Their masses will have to get balanced. Mass of an object or mass of objects is neither created nor destroyed. It remains the same. It's a universal principle that chemistry has made before us. So now it is MgO here, Mg, here it is not O, it is O2. So one atom got represented here, where should the other atom go? Now we put coefficient 2 here. Coefficient 2 here. Now two atoms of oxygen, they are neither gained nor lost in this reaction. You have two atoms of oxygen. It's not lost. But magnesium atoms have gone up to 2 now, from 1 to 2. Here we have only 1. Now we have to write 2 here. It was not there earlier. We write 2 here. Now the equation got balanced. 2 mg, 2 mg, O2, 2 O. When you have written coefficient here, it encompasses the entire compound. 2 mg atoms, 2 O atoms. So this is how the equation is balanced. The equation is balanced. In the case of all the chemical equations we write, as we turn into the symbolic form, it is absolutely essential that the left hand side and the right hand side, they are balanced with each other. Otherwise, we call the equation as a skeletal equation. If you don't write 2 here, 2 here, it becomes a skeletal equation. It doesn't have the flesh added. It's a skeleton. So we add 2 here and 2 here. Now it is a very well balanced equation. Okay, we come to the next. Here we have zinc. This experiment too we had done yesterday. Zinc is mentioned by the symbol Zn. You say Zn or Zn, as you say, it's fine. It is zinc. You may ask me, why not Zi? It's convenient to take N. The moment you say Zn, you feel, oh, it is zinc. It's an abbreviation that stands for the element zinc. That's how scientists have named them all. Plus, we have the dilute acid here, H2SO4. 2 atoms of hydrogen, 1 atom of sulfur, 4 atoms of oxygen, H2SO4. Dilute sulfuric acid acts on zinc to give us zinc sulfate. Zinc, Zn, 1 atom, S, 1 atom, O, 4 atoms. So this SO4 radical has come and it has got bonded with zinc. So it is ZnSO4 and H2 got released. H2 got released from the bonds it had with SO4 radical. And we have marked here, we have an arrow mark. What does the arrow mark show? Arrow mark says it's a gas. The matter that's formed in the gaseous form moves up, goes up because it's a gas. So by drawing this arrow mark upwards, I am designating or telling the readers that gas hydrogen got liberated. Now here there is no question of balancing. You may ask why. Let us check up. Always you start checking up where that compound, which is the most complex one in the equation. Here if you see, you can see ZnSO4 or H2SO4. Take any one of them. Let's take ZnSO4. From the products better we take. Because as the products got formed, whether it got maintained or not, that's what we want to know. ZnSO4. Zn is here, balanced. Nowhere else you have zinc here. Then S is here. O4 is here. Where is H2? It got released as gas here. H2 is here. So, no atom is lost, no atom is gained. On the reactant side and on the product side. The equation is a balanced, very well balanced equation. We need not add any coefficient here. We call such numbers as coefficients. In mathematics you might have learned. I don't want to go to that. Okay, this is a balanced equation. So, as chemistry students, you ought to learn as to how you should balance an equation. It is the right time. You are learning the basics of chemistry. It is the right time now. Once you come out of this video, sit yourself, take down this. You can remove all the coefficients, keep 3 or 4 equations and start laying the coefficients yourself. You immediately come to know. It will be difficult for you to write the equations as such all of a sudden. It takes some time. See that you get exposed to these equations every day. You cannot remember days reading on the previous day of the exam. You won't remember at all. That too, scores of equations like this. You should take a sheet of paper or a rough book and start trying. Wherever you get into a doubt, go through the main list what you have, check it, or with your textbook you check it. We have not gone to any equation other than what's been given in your textbooks. We have covered them all here. We will discuss all of them today one by one. No doubt should remain as such with you. So this is Zn plus H2SO4 gives us ZnSO4 plus H2. If you want to put it verbatically, we can say zinc plus sulfuric acid dilute gives us zinc sulfate plus hydrogen. Shall we move ahead? Yes, we have a complex equation here. Many of the equations here are very simple. I have taken because we can discuss further with these equations. See here, Fe, ferrum, ferrous, ferric, fer, that word starting from Ferr. It stands for iron. Fe is iron. What is it? Yes, we have written here. See, this is another symbol used while writing equations. Don't worry about 3 now. We will take only Fe. In bracket we have written S. Small s. Small s stands for solid. You know, solid, liquid, gas. These are 3 types of matter. 3 kinds of matter. Ice is solid, water is liquid, steam is gaseous. It is in the vapor form. So solids are written by the symbol small s. You will be able to tell now. Liquids are written using letter L. Gases are written using letter G. When I write this, they should be in bracket. Because if you don't put the bracket, it becomes one with Fe, and we read it as ferrous sulfide then. Ferrous sulfide. It will be another chemical. That's the reason why you should put bracket here. When you put bracket, it has nothing to do with the element. We take it like that. Okay? Iron. Fe is iron. Iron. These are Greek terminologies. Fe is the short form, abbreviation. Plus 4H2O. I'll make a small correction here. I have written it as yes. It's actually we should write it as G. I'll tell you why. You may say, sir, what is a liquid form? Why G? Why gas? In this equation, water reacts with iron in the form of vapor. See, there is water content in the air. What do you call it as? Moisture. You say the air is moist. If there is too much of moisture in the air, you start sweating. In summer, you start sweating. Moist air. If you go to the coastal line, Mangalore, Cochin or Karwar, you sweat and sweat like anything. This is the right time. Summer. Go to the seashore, people can see you sweating everywhere because the air is moist. Why is it moist there? why is it not that moist here? Here air is dry, almost dry. You don't see anyone sweating like this, droplets coming down. It is coastal line. You have the sea right on the edge, from north to south. The vast sea full of salt water. So air is full of moisture. So naturally when you sweat, you give out a lot of water all over your body. Your clothes will be wet. The dress you wear, it will be wet. You feel tired. Okay, here water is in that form. The water, what we mean now, that acts with iron is in the form of gas. See, we have the window, you have the iron bars. They don't come in contact with water, let's say, but still iron will start getting rusted. We have not painted the iron bars properly, they get rusted. From where did it get water? It got that water which was in the air. Moisture in the air. That's why we have written G. Water in the form of gas. Water in the form of moisture in the air. I think you would appreciate it. Somebody would just read like that. How will they read? If G is not there, iron plus water, they will read. No, it's not water. Iron plus moisture. The vaporous water, water in the form of vapor in the air, they react and we get iron oxide. We won't go to ferrous and ferric now, unless there is a lot of confusion. I will call it as iron oxide. Iron plus vapor or moist air, moisture in the air, gives us iron oxide plus hydrogen gas. Hydrogen gas is getting liberated. Now we will go into the details. Fe plus H2O, I told you, forget about this. This coefficients you will see later. H2O gives us Fe3O4 plus H2. Now we have to balance it. Balancing the equation. Iron which are left in the open or when the air is moist. If you go to coastal line, you just discuss with people here, they always complain of rusting iron. Oh, you can't use any iron gadget here. It gets corroded easily. They use the word corroded. Yes, corrosion is also the right word for rusting. If you have an iron bar and it starts getting rusted, it starts getting corroded year by year, becomes thinner and thinner, and ultimately one day it will break. That's, you call it as corrosion. So iron plus water gives you iron oxide plus hydrogen. Now let's see which one is the most complex compound here. Iron, no. Water, no. Here H2 symbol. We feel if it is iron oxide, Fe3O4. Let us start here. In the reactants, it's only here where you have Fe3O4. Fe3 is here. That means 3 atoms of iron. 3 atoms of iron. Whether it's balanced here? No, here I have only 1 atom of iron. So I add here 3. Iron has got balanced. Iron atoms, their position is balanced. Fe3, 3 Fe. Okay, next, that pertains to the reaction carbon monoxide. C stands for carbon, O stands for oxygen. It is carbon monoxide. Mono means single atom of O. Carbon monoxide, it's a gas. So in bracket we have mentioned this symbol. It's in the form of gas. Plus 2H2. 2 molecules of hydrogen. H2 is 1 molecule. H is atom. When I say H2, it's a molecule. Two hydrogen atoms, when they bond with each other, it becomes a molecule. How many such molecules are here? Two molecules are there, 2H2. Again, hydrogen is a gas. Now in this equation, what happens? You have the arrow mark here. Above the arrow mark, we have written another specification. 340 atmospheres. ATM stands for atmospheres. That means you are told how much of pressure will be there, how much of pressure is required for this reaction to take place. Now the pressure of the atmosphere around us, the weight of the air columns on our shoulders, it amounts to 1 atmosphere. That's the unit. Unit of pressure is 1 atmosphere. You have to add up 340 such atmospheres. It's a very, very heavy pressure. Only under specially set lab conditions you can go for a pressure of 340 atmospheres. At a pressure of 340 atmospheres, carbon monoxide combines with hydrogen to give us CH3OH. CH3OH is methyl alcohol, or we also name it as methanol. Methyl alcohol and methanol are one and the same. Usually people say methanol instead of saying methyl alcohol, and some may not like to stress on that word alcohol every time. So methyl alcohol is a liquid. Two gases combine to give a liquid, and I have named it here as methanol. Of all the alcohols, methanol is the simplest alcohol. That means most simple alcohol. There are varieties of alcohols. Of all of them, this is the most simple one. So here you have a specification written here. In brackets you have the state of matter mentioned. So as you read this equation, everything becomes clear. Now the only aspect we have to check is balance. I have told you, when we want to balance an equation, we have to go for the most complex substance there. One is carbon monoxide, another one 2H2, that's hydrogen, the third one CH3OH. Without any doubt we can say CH3OH is the most complex one. The very writing tells it. So we will start from here. Now CH3OH molecule is made up of three kinds of atoms. One is carbon, another one hydrogen, third one is oxygen. This is again hydrogen. Okay, we will start with C now. How many atoms are here? One atom. Now on this side there is one carbon atom. 1C, balanced. Come to H3 now. H3 here, H here. Put them together. 4 atoms of hydrogen. Look here. H2. How many molecules? 2. So in each molecule you have 2 hydrogen atoms. In 2 molecules of hydrogen, you have 4 atoms. 2 into 2. Here you have 3 plus 1, 4. Here you have 2 into T, 4 hydrogen atoms. It's balanced. So what's left out is 1 atom of oxygen here. It is balanced here. 1 atom of oxygen. With this, what can we say? Entire equation, the right and left sides are well balanced. We move on to the next one. This is a little complex for study, but it's an important equation of a process that goes on around us in all the plants in the presence of sunlight. So the specifications are written just above and below the arrow mark. Above the arrow mark, what is it written? Sunlight. This reaction takes place only in the presence of the solar energy, sun's rays, sunlight. Below, what is there? You need a factory where the entire process goes on. That is chlorophyll. Chlorophyll is a green pigment we find in the leaves of the plants. It gives green color to the plants, a very important substance where the entire light reaction takes place. The reaction that can happen only in the presence of light. Chlorophyll. So this we have written here. So it's a specification that one should read as he reads the equation. Now let's go by the equation. 6CO2, in bracket is given AQ. AQ stands for aqueous. Aqueous. It is in solution with water. CO2 is dissolved in water. This AQ tells. A solution of CO2, carbon dioxide. 6 such molecules. In each molecule of carbon dioxide, you have 1 atom of carbon, 2 atoms of oxygen. These two tells that. Here you have coefficient 6. Coefficient 6. What does that say? There are 6 molecules of CO2 involved in this reaction. Plus 12 molecules of H2O. 12 is the coefficient. It says there are 12 molecules of H2O, water. Each molecule of water is made up of 2 atoms of hydrogen, 1 atom of oxygen. So these are the reactants. We have 2 reactants, carbon dioxide and water. Coming to the other side of the reaction, we have C6H12O6. What does that specify? It is glucose. Molecular formula of glucose is C6H12O6. You all have seen glucose. Glucose comes in packets. If somebody is not keeping well or is too weak because of the high temperature he is running, you give him a spoonful of glucose with a glass of water to drink. He will be able to recover to a certain extent. So that's glucose. Glucose is prepared by plants in the chlorophyll pigment. This is the key aspect in this reaction. C6, 6 carbon atoms, H12, 12 hydrogen atoms, O6, 6 oxygen atoms. Together you call it as 1 molecule of glucose plus 6 O2. You know, when the photosynthesis takes place in plants, the gas taken in is carbon dioxide. The gas given out is oxygen. This we have already learned. Right from 3rd or 4th standard you start learning about the photosynthesis reaction in plants. Photo stands for light. Synthesis of a new chemical in the presence of light. So photosynthesis. Here 6CO2, aqueous again. Oxygen is given out by the plant in the form of a solution, oxygen dissolved in water, plus 6 H2O. O2 we have specified separately, we have water mentioned here. 6 molecules of water, it is in liquid state. So everything you come to know, which was said, all these are in liquid state except for glucose, which is in solid state. What is left out now? The portion that we have attended is the balancing. It's not that easy as we find 2Mg plus O2 here. It's a little complex. You have to attend, concentrate, and later you should be able to write the equation on your own, not by hearting. Now 6CO2 plus 12 H2O gives 6 C6H12. No, don't learn that way. You should be able to know the molecules and these coefficients you should be able to work out and put. But if you keep on working, automatically it comes to gets into your memory, and as and when you require, you will be able to substantiate. Let us see which one is the most complex one in the entire equation. We have to start from there. C6H12O6, that's glucose. We'll start from here. C6. How many atoms of carbon? 6 atoms of carbon. Go to the other side of the equation. Let's see whether it's balanced. Here you don't have carbon. Here you have 6 atoms of carbon. 6 atoms of carbon. So it's balanced. Carbon is balanced. 6C. Here too. Here it is C6. Because it is in combination with other atoms. So the coefficient 6 is written here down below. Now we will take up the next part. H12 here. H12. It's not over just here. Here too you have H2. This 6 is not written here, let's say. Not written here. Now we have to find out. 12 H atoms, 2 hydrogen atoms. Together it is 12 plus 2, 14 atoms. Let us see here. 12 into 2, it is 24. Here, 2 into 6, we are not multiplying. You have to work out. Now, here it is 24. 12 into 2, you have to always multiply, I have told you, to find out how many atoms are there. 12 atoms of hydrogen. Here you have none. Coming here, 12 are covered here in glucose. How many are remaining? 12. Here, 2 is already there. Now, to make it balanced, you need 6 here. 6 into 2 is 12. So, you write the coefficient 6 there. Hydrogen is balanced. With a little bit of practice, you get it. Now, what is left of is oxygen. O6 here. Here you have O2. 6 we are not written still. We don't know. We are not written. Though it is complete here, let's take it for granted we are not written. How do we get that 6? 6 here, 2 here, it is 8. Yeah, 8. Here if you say 6, here 2, 6 coefficient covers entire CO2, when you multiply it will be 12. 6 into 2 is 12. Here 12O. This 12 coefficient covers the entire H2O molecule. So 12O here, 12O here, 12O here, all together again it is 24. 24. Let us see here. 6 here. Take off. 24 minus 6, 18. 6 here, 6O. Another 6 you take away. 12 remaining. Come here now. 2 is there. 12 divided by 2 is 6. You write 6 here as coefficient. You got 12. So 6 plus 12 plus 6. Altogether it is 24. This is how you will have to balance. Entire equation is very well balanced. If you keep trying it out again and again, the whole equation will be in your memory then with the coefficients. You need not work out at all. We come to the next one. It's an experiment wherein iron is made to react with CuSO4. Fe is iron, you know. F capital, E small. Ferrous, ferric. It's a Greek term to begin with. From there we have capital F and small e. Here you have CuSO4. Cu stands for cuprous. Cuprous means copper. Copper sulfate. It is even called as Mailututta. Copper sulfate. What reaction will be there if iron reacts with copper sulfate? See here we have copper sulfate. Can all of you see? It is blue colored. It has a shiny. Looks nice, but it's a poison. If you have copper vessels in the house, old copper vessels, which you might have kept in the attic, huge ones, when people have to be fed, guests have to be fed, those vessels are taken out and used after wash. But if you don't attend to the health aspect, there will be a green or bluish coating inside. Actually, once in 2 years or so, you have to get it coated properly, inside part. If you don't do it, this will be there. With your nails, if you scratch, you get it out. You will be able to take out, it's a poison. So, copper sulfate crystals, these are crystals. You got that sonorous sound as I put it back. Sonorous sound, a pleasant sound it is when the crystals form. We have taken some crystals and we dissolve it in water. When it dissolves, you get copper sulfate solution. We have already got it dissolved for you. So this is CuSO4 solution. What's been mentioned here? A CuSO4 solution has a sulfate radical in it. Copper is the metal and a sulfate radical. SO4. One atom of Cu, one atom of S, sulfur, 4 atoms of oxygen. It is CuSO4. Now that's the makeup of the solution. And you have water there. Water we have not mentioned there. There is no, we get the water just as it is at the end. It will be there. It will not undergo any chemical change. So we need not mention water there. So this is CuSO4. Now we need iron. I have taken some 2 iron nails. We have kept it tight so as to save time. 2 nails we have taken. Both the nails, they have the shine. New iron nails if you get, they will have this metallic shine. You see? We have tied the 2 to a thread. I will keep this vessel here and make these 2 nails get submerged in a copper sulfate solution. See. Now both the nails are submerged in the copper sulfate solution. Let's leave it there like that for about a minute or so. It won't take much time. There will be a very quick reaction and we find the change. I won't tell you what the change is. Let it be a surprise for you. So in this reaction, the reactants are iron and copper sulfate. On this side, here what happens, this SO4 will go and join with Fe. And Cu will get separated. Copper will get separated. Where will it go? You come to know now. See. A big surprise for all of you. The color of the nails has got changed. They had a metallic shine earlier, now they have a copper cover. They look like copper nails now. It won't come out, see, they don't come out, the color remains the same. If I leave it for another 1 hour or so, the nails will have a beautiful coating of copper. From where has the copper come? Copper has come from the copper sulfate solution. Copper got removed there by iron. Iron and copper, when they are compared with each other, iron is stronger than copper. It will displace copper there. It will displace and occupy that place. So where should copper go? Copper comes and gets accumulated on iron because it has been made free. It gets accumulated there. So that is the reaction. We will leave it here for some more time. We can have one more look at the end of the period. Now let's say that the equation is balanced. This is FeSO4, ferrous sulfate, or you can even call it as iron sulfate. Iron sulfate. Plus Cu is copper. Now here there is no need to balance it all. It is already well set. You have one atom of Fe here, iron, one atom of Fe here, one atom of Cu here, one atom of Cu here, one atom of S here, one atom of S here. O, four atoms, O, four atoms. The left hand side and right hand side of the equation are simply, they are well balanced. You need not add any coefficient anywhere. Already it is a balanced equation. So how do we read? Iron plus copper sulfate gives no conditions. We don't heat or no pressure required, nothing of that sort. It gives ferrous sulfate, or you say iron sulfate plus copper. Now this is a displacement reaction too. We call it so because iron has displaced copper from copper sulfate and iron has occupied that place. Do you see that here? Iron displaces copper from the copper sulfate solution and occupies that position. Such a reaction is called as displacement reaction. One chemical displacing another chemical or element, whatever it be. Here we don't say chemical, we can say element. Element iron has displaced copper from copper sulfate solution. And various types of reactions we study next, there you will come across displacement reaction. This is one of the best examples for displacement reaction. If we leave one house and go to another house for our permanent stay, regular stay, we say we got displaced. I got a job in the neighboring other city, so I too got displaced, my family got displaced, I had to shift. We come here. We can go a little faster now because you know what is balancing. What you have to do? Once you go home, take a few sheets of paper, start working out each of the equations or chemical reactions on your own. If you have to get mastery in chemistry, you have to be good at equations. You have to be good at symbols. And right hand side and left hand side have to get balanced whenever you write an equation. If you don't get it balanced, we call the equation as a skeletal equation. Skeletal. No difference. See, our body and our skeleton, we just compare. Skeleton will not have flesh on it. Now whatever coefficients and all this you add, it is in order to make it more meaningful. You exactly know how many molecules do take place, how much is the production, everything gets clear. We come to the first one now. Here we have taken quick line. A quick line here. Quick line is calcium oxide. Calcium oxide. If you go to rural areas, there they will be dealing with it. When you want to get calcium hydroxide made, or in normal language I do not know, sunna, they call it sunna or chunnam. These are the words they use. If you like to have a treat of betel leaves and aracanite pieces, they apply chunnam or calcium hydroxide on the betel leaf. First of all, that's the job they do. Then they keep one or two aracanite chips there, fold it properly, roll it, then keep it in between the teeth and they start chewing. So calcium hydroxide has a key place there. We can get calcium hydroxide from calcium oxide. This is not that powerful because this chemical we have kept it in the lab for quite a few months. But if you go to those who deal with betel leaves and betel trees, they will get calcium hydroxide made afresh. To make fresh calcium hydroxide with all strength in it, you have to go for calcium oxide, which is fresh and very active. What we do now, in a test tube I take a little amount of calcium oxide. Here it's in powdery form. Usually when you get it from layers of soil, you have to dig soil. People who deal with it, they know it very well as to where they get river banks and all they do get. And if you hold it in the hand, calcium oxide, within half a minute you feel your hand burning. It becomes hot. You drop it. What a surprise you get in nature. If you hold it, it doesn't excuse you. You have to drop it. Because calcium oxide reacts with water. You can make out here. Water is a liquid. Calcium oxide is a solid. How did I come to know? You saw it now. Otherwise this yes tells us it's solid, it is in solid form. So what should I do now? I have to add a few drops of water to it. All these experiments you can again try. You saw all of a sudden it sprung up. I told you, calcium oxide is not that fresh. It's already hot here. See, calcium oxide has put forth its features. When it combines with water, it's warm. It has given out heat. As calcium oxide reacted with water, it has given out heat. Now such a reaction, we call it as exothermic reaction. Exothermic reaction. See, we have written heat there. Calcium hydroxide, that is slaked lime. This calcium oxide, we call it as quicklime. Quicklime reacts with water to give slaked lime, calcium hydroxide, and heat is liberated. So we call this reaction as exothermic. Okay, now let us see whether the equation is balanced. CaO plus H2O, CaOH twice, OH we call it as hydroxide, plus heat. Heat doesn't come in our balancing aspect of the equation. So already it is matched, very well balanced. Ca, here you have one O, another O, here you have O, you have 2 outside the bracket here, so 2O, 2H, 2H is here, 2O, 1, 2. The entire equation is very well balanced. Let's move on to the next. Zinc plus hydrochloric acid gives zinc chloride plus hydrogen. We have already written one equation here. Zinc plus sulfuric acid gives zinc plus sulfuric acid, dilute sulfuric acid gives a zinc sulfate plus hydrogen. Instead of sulfuric acid, we have used hydrochloric acid here. Instead of sulfuric acid, hydrochloric acid. Again the reaction is of the same kind. You get hydrogen getting released. So Zn, H, 2H, here we have H2, 2Cl, this coefficient pertains to the entire molecule. So 2Cl, here it is Cl2. The valency of zinc is 2. That's why it is not ZnCl, it is ZnCl2. One atom of zinc combines with 2 atoms of chlorine. So the equation turns to be, or the formula turns to be ZnCl2. And here we have an arrow mark upwards to tell that it is a gas. We move to the next. It's a very simple one. 2H2O gives 2H2 plus O2 when electricity is passed. So here I can write electrolysis. When electricity is passed through water, the molecules of water start getting divided into hydrogen and oxygen. Under no other circumstance, molecules of water can be made to get separated. You can't make them get decomposed. They don't get separated. Electrolysis. With the help of electricity, you bring about destruction of water molecule. Lysis means destruction. Lysis. You destroy each molecule of water by passing electricity. So it is called electrolysis. Here 2H2, 2 into 2, 4. 4 atoms of hydrogen. Here 2H2, 4 atoms of hydrogen. O, 2O, coefficient is 2. So here it is O2. It is balanced. I can add here an arrow mark. Here too I can add an arrow mark because both these happen to be gases. Water is a liquid. Now it's a complete equation. Next one is C plus O2. C is carbon. Carbon plus O2 gives CO2, carbon dioxide. Again 1C, 1C, 2O, 2O. It is a balanced equation, a very simple equation. If you burn carbon, the gas that evolves is carbon dioxide. That's why we say we should not burn wood as fuel in the house. In almost all the houses, people have stopped burning wood because we know that carbon dioxide is released. Along with carbon dioxide, even some poisonous gases in traces, they come out. It's not good for those who work in the kitchen round the clock. So even where Adivasis, these tribal people do stay, government gives them free gas cylinders and tells them don't cut trees for burning and burn wood to get the heat or for cooking. We give you free gas. You use this gas and you see that trees are protected. You conserve trees. You be the guardians of the forest. So they are given the responsibility and they are told not to cut trees for fuel. So C plus O2, CO2. Such equations, let them not just remain equations for us. They carry a lot of stuff with them. That stuff we should be good at. Next, CH4 plus Cl2. A little tough, tougher than other equations. CH4 is methane. You remove one H here and add OH, it becomes methyl alcohol. Methyl alcohol. We have already dealt here. Methanol. Methanol is methyl alcohol. Same thing here. CH4 methane plus 4Cl2 chlorine. It gives us carbon tetrachloride. 4 stands for tetra. Tetra. Carbon tetrachloride. That way is it easy to remember. By saying that, you remember the symbol too. Carbon, C, tetra, O at the end have to know 4. Then chloride, Cl. CCl4. Easy to remember. CCl4 plus 4HCl. 4 molecules of hydrogen chloride get liberated. Hydrogen chloride. So C here 1. This is here 2. You should not have. 1 C here, 1 C here. Balanced. 2 Cls here, 2 into 4 is 8. Chlorine atoms are 8 here. 4 chlorine atoms here, 4 chlorine atoms here. 4 Cl, Cl4. 4 plus 4, 8. Here you have 4 into 2, 8. So it's balanced. What is left out now is H. H4 here, 4H here. Always remember, whenever there is a coefficient, the coefficient belongs to the entire molecule, not just to H. Whatever you write here, that pertains to only that element, not to the entire molecule. So methane plus chlorine gives us carbon tetrachloride plus hydrogen fluoride. Next, this reaction we will be learning in the next lesson too. We just read it out now. BaCl2. Ba is the symbol for the element barium. Ba. Cl2, barium chloride, plus aluminium sulfate. Al is aluminium. Sulfate, SO4, sulfate. The valency of aluminium is 3. Valency of SO4 radical is 2. So they exchange here. So it becomes Al2SO4 thrice. SO4 thrice. Entire SO4 thrice, 3 times. Gives AlCl3 plus 3BaSO4. You see the beauty here. This is, we call it as radical, Cl2. Here the radical is sulfate. They exchange. Cl2, when barium chloride and aluminum sulfate come together, this chloride goes here, sulfate comes here. Look there, is it? Aluminium chloride plus barium sulfate. This we call as double decomposition. See, water dividing into hydrogen and oxygen is decomposition. It decomposes. Here, it's not one chemical that decomposes, 2 chemicals decompose. So we call double decomposition. Barium chloride decomposes, aluminium sulfate too decomposes, and they exchange their radicals and you have the products. These two are products. Now let's check. Ba3, here 3Ba. Cl2, here 3 coefficient, 3 into 2 is 6. Here Cl3, 2 is here. Vice versa from there. So 2 into 3 is 6. Chlorine is 6. Come here, Al2, 2Al. Matching. Yes, thrice. This 4 doesn't belong to this. Yes, 3 sulfur atoms. Here let's see, 3 sulfur atoms. O4 thrice outside. Yes, thrice it comes, but this 4 won't act on it. Now O4 thrice it is. 4 into 3 is 12. So 12 atoms of oxygen should be there on the other side. We'll see. O4 coefficient 3 into 4 is 12. So 12 atoms here, 12 atoms here. That too got matched. Balancing the equation, it is actually fun once you know it well. These are the rules. Other than these, you don't have any additional rule. It is just fun. You play with the different chemicals, make the left and right sides match with each other. You should take it as fun. Should never consider these jobs as a burden. Move to the next. Simple. We have sodium. In the coming videos, I will be showing the experiments. If too many experiments are added up, then the lesson will just go on getting swollen too much. That may not have an ear to hear. 2 Na plus 2 H2O, 2 Na, you have here 2 Na. 2 H2, H 4 atoms. H2 here, 2 H here, 2 here, 2 here, 4. Now what remains is 2 O here, 2 O here. Equation is balanced. So sodium, it's a metal. If you take a pinch of sodium and put it in a basin of water, sodium will start rumbling around with a lot of noise. It starts reacting with water, and sodium hydroxide will get formed and hydrogen will get liberated. That's what you see here. Sodium plus water gives you sodium hydroxide. That water in the trough will become sodium hydroxide, and hydrogen is getting liberated. It's a guess. We come to the next. Again a double decomposition. Double decomposition. BaCl2, just like here. Here instead of aluminum sulfate we have taken sodium sulfate. Cl2 goes here, SO4 comes here. So when we deal with double decomposition in the next lesson, I will be showing these reactions to you. Here you see SO4 has come here, it is BaSO4. Cl2 has gone there, it is Cl. How is it 2? Coefficient is 2. Na to 2 Na. Cl, Cl2, it is 2 Cl. So right and left hand sides are matched. Next one is NaOH plus HCl. Again a double decomposition. Na radical is OH here, HCl radical is Cl. They just exchange. This is a base, this is an acid. Acid and base, when they come together, you get salt and water. NaOH is a base. HCl is an acid. NaCl is a salt. H2O is water. So OH and Cl, they exchange. It becomes NaCl plus HOH. 2 H's are there, it becomes H2O. We need not check at all. It's just the radicals are what exchange. Everything is there. Na, O, H, 2 H's, they have come together here, H2, and Cl is here, Cl is here. Sodium chloride, sodium Na, natrum. Natrum is the Greek word. First letters are Na, capital N, small a. So sodium chloride plus water. Now last one here, CaO, calcium oxide. The same reaction we have written again. It gives you CaOH2 plus we can mention heat. We have checked it here already. It's been written in a simple form here at the end. Now this is all about how chemical equations are balanced. If you don't balance an equation, it becomes a skeletal equation. Skeletal equations do not have value in chemistry. In the beginning stages you can write, but as you study a few months, as you come to the end of the year, you should be able to write the equations in such a way that both right and left hand sides, the products and reactants should be able to match with each other. Shall we close here? Thank you.